The next thing we're going to take a look at is intervals on which a function is increasing, decreasing, and constant. And so I've actually put up a graph here that would be rather relevant to us right now. I've put time on the horizontal axis, and I put new infections per day on the vertical axis, talking here about COVID-19. Okay. I've just made up this graph. I'm not claiming that this represents any particular area, but you've certainly seen plenty of curves like this if you've been watching the news. Couple of things to point out. First of all, anytime you see something like this, where this is the new infections per day, technically, if I were graphing this, I would only have points really at integer values. 1 day has passed, I've got a point at 1. 2 days have passed, I've got a point at 2. So realistically, I'd have a graph that just consisted of a bunch of isolated points, each 1 day apart. Most of the graphs that you'll see on the news have been smoothed out, they've just connected those dots. Okay. Another thing to point out is that it's really important that you, when you're reading a graph and interpreting it for a real world situation, that you read what the axes are representing. I should probably say that time here would be measured in days. Okay. This is new infections per day. So when it looks like it's leveled out here, some people would say, oh, great, we've leveled out the number of people who are sick. Nobody new is getting infected. That's not what this says. This says the number of new infections per day is constant. But there are still new infections each day, so the infection is still spreading. That would be very different from a graph that just said total number of infections that we have. If that leveled out, that would mean that there were no new infections. But here, the only thing that would mean that there were no new infections is if we actually dropped down and touched the horizontal axis. That would mean there were no new infections per day. So you want to be very careful about not making assumptions about what it means. You've got to make sure you're looking at what is being measured. Okay. Another thing to point out, when we're talking about things increasing, decreasing, and constant, we always read our math graphs from left to right. Okay. So just going with a very intuitive sense of what it means to be increasing, we're pretty clearly increasing over here because we're going up as we read this left to right. Now, if instead of representing new infections per day, if this was representing the shape of the land so that this was some sort of a hill, as a cyclist, I don't read hills left to right because I realize that hills are two-way. So I might say this hill looks like, oh, it would be horrible to bike up, but it would be kind of fun or maybe a little bit scary to turn around and bike down. I recognize that with hills, you can go up them and then you can turn around and you can go the other way and now it becomes downward. But when we're reading math, we always read things left to right. Okay, so we're increasing here. Assuming this is actually completely flat on the top, we'd be constant here and then decreasing here. And you hear a lot of talk on the news about leveling the curve, getting to the point where here the number of new infections per day is increasing. So not only are more and more people getting infected, but they're getting infected at a faster rate. Once we level the curve, if this is the curve we're talking about, and there are lots of different curves that you might see, so it's important to know which one you're talking about, leveling the curve here would be saying, okay, there are still new people getting sick, but the rate at which they're getting sick has leveled out. They're now getting sick at a constant rate. Then we can turn a corner, and now the rate at which new people are getting sick is decreasing. Still, more and more people are getting sick, but hopefully some of those who previously got sick are recovering and getting better, and now we're starting to actually control the spread of the disease. Okay. A graph like this is incredibly important in determining what it's safe to do. Right now, you're taking this class online, and you're taking this class online because it is not currently safe, or at least, actually it would be wonderful if it is now currently safe. But at the time that we had to plan for this semester, it was not safe to have people together in confined spaces. Hopefully that has changed. If it hasn't changed already, hopefully it will change soon. But we really need to have more testing. We really need to have a vaccine or a cure for this disease before it's going to be safe for us to go back to meeting in person. So whether something is increasing, decreasing, or constant can have real important ramifications for us. In the business world, people often want to know, when is my profit increasing or decreasing and constant? In making plans for what you're going to do with the company, you generally want your profit to be increasing. You generally don't want your profit to be decreasing, but you might want to decrease your costs. Okay. So very often we're going to care about this. Now, this class is pre-calculus. In calculus, you're going to learn how to look at the formula for a function and do some algebra and some calculus to, just working with that formula, be able to figure out whether a function is increasing or decreasing. At this point, the only sort of function that we can do that for would be a linear function. But if I had something like f of x equals 3x plus 2, and g of x equals 5x minus 1, and h of x equals 2, okay? Well, all of these are examples of linear functions, so they're all linear. For this one, the slope is 3. That's a positive slope, so this function would be increasing everywhere. Notice I didn't have to graph it. I was able to just look at the formula. Because it had a positive slope, I know it's increasing. I'm sorry, I meant to make that b g of x be negative 5x minus 1. So again, that's a linear function. The slope is negative 5. So with a negative slope, that is going to be decreasing. Okay. This is also a linear function. This is a constant function. But that is a linear function where the slope is equal to 0. Okay. So this is, of course, constant. Okay. Now there, I didn't need to look at the graph in order to know whether the function was increasing or decreasing, because it was always doing the same thing, and what it was doing was encoded in the slope. With any function that's more complicated than that, like the squaring function, if I look at f of x equals x squared, that's not always increasing or always decreasing, because it changes what it's doing. Reading from left to right, the squaring function is initially decreasing and then it's increasing. Don't get confused by this arrow here to say, oh, that arrow's pointing up, so it's increasing. That arrow just indicates that we're going on forever and ever and ever. But notice this arrow is pointing up and to the left. We don't read functions going leftward. We read functions going from left to right, so going rightward. So this function is initially decreasing, and then it switches and it's increasing. So it does a little bit of both. Okay. Now, since we're familiar with the graph, we can see where it does each of those things. But in calculus, you'll actually learn how to work with just the formula for a function to find the intervals where it's increasing, decreasing, and constant. We're going to work with just the graphs of functions to get used to that concept of when is something increasing, when is it decreasing, and when is it constant. What we're going to need to do is formally define what's meant by these terms. We sort of have an intuitive notion. We're decreasing here because we're going down. We're increasing here because we're going up. But we're going to give a formal definition for that, and that's going to have an interesting technicality, and we'll take a look at that in the next video.